Good day to everyone. I am Romel Jeremiah B. Trinidad, and I will be discussing about the introduction on our paper review, which is Synthesis of Smart Coating for Furniture Textile, their flammability and hydrophobic properties. So to start off, what are textile fabrics? Textile fabrics are composed of different textile fibers. Such fibers are cotton, polyester, and wool fibers, and many others have been used. So textile fabrics is actually used in various industrial and domestic applications. However, with their wide use also comes in some problems. Two of the main problems encountered by textile fabrics are low thermal stability and low hydrophobicity. Because of this, its applications were restricted in the industry. That's why to overcome this, some researchers are actually finding a way to synthesize the textile fabrics so they could increase their thermal stability and also increase its hydrophobicity. So one solution to address this problem is the incorporation of phosphorus-based material to increase the flame retardant of the textile fiber. However, with the application of this, it also causes some problems. And one problem is the loss of mechanical properties. With the use of the phosphorus nitrogen based material, we were able to increase the flame retardant. However, we lose the mechanical properties. That is why a solution for this could be the incorporation of spherical inorganic nanoparticles and nanotubes. So these have been used in textile treatment, and this is actually used so that we can achieve the comfortability property on textile materials. And such example of this is the TiO2 nanoparticles, the ZNO, and the graphite. So graphite is a carbon allotrope. When we say allotrope, it is a physical form. It can be two or more different physical form in which an element can exist. Like for carbon, we have graphene. And graphite are actually sheets of graphene stuck together. So we use graphite because of its abundancy. And graphite actually has a good flame retardant additives. And it is used in many various polymers. And with good flame retardant means we also increase the thermal stability. It is also good to take into account that if we increase the thermal stability of the textile fabric with the application of flame retardant materials, we are also decreasing its mechanical properties and comfortable properties. That is why when we are synthesizing, we must also take into account not only the increase in thermal stability, but we must also find a way to sustain maybe the comfortable properties and its mechanical properties, and if better, to improve it. And for this paper, we have the new smart flame retardant system we will use, which is a mixture of incorporation of graphite, ammonium phosphate, and 3-trimethoxyl-propyl ethylene diamine, and titanium dioxide nanoparticles. So our objectives with the new flame retardant system would be study the following: its flammability, thermal stability, mechanical properties, and hydrophobic properties. We will see in the stated which one improves or if it retains, and we will see overall if the incorporation of the flame retardant materials are actually successful in the textile fabric.
The materials used are commercial fabrics with the following composition: polyester 35%, microfilament 25%, fibrin 25%, and wool 15%. Commercial binder was also used, and commercial graphite powder and ammonium phosphate, TiO2 nanoparticles of an average particle size of 20 nanometers, TMSD, and deionized water. So for the general workflow, first, what was done was the synthesis of the coating dispersion, BGR TMSD AP and BGR TMSD AP TiO2 NP. And next is the preparation of textile. And then after that, they proceeded to the characterization. Here we have the schematic diagram depicting the synthesis of TBGR, TMSD, AP, TiO2, NP textile fabrics. So we can see here the synthesis of the coating. The smart coating was developed as represented here. The GRAP, TMSD, and TiO2NP were dispersed well in the solution using the ultrasonication process. And then the furniture fabric was coated with dispersion. After that, the fabric was treated, dried, and cured. So for the synthesis of coating dispersion, in a beaker containing 50 ml deionized water, 4 grams of binder was dissolved, and constant mass ratio of GR and TMSD were dispersed as shown in Table 1. And then variable masses of AP were added in the dispersion. For the last sample, FTC4, we added 0.2 mass ratio of TiO2NP. After that, the dispersions were exposed individually to ultrasonication for 30 minutes at 50% output for preparation of good dispersion. For the preparation of textile, sample dimension of 20 cm by 20 cm of commercial fabrics were immersed in each coating individually for 10 minutes. The samples were then removed and squeezed out. This process was repeated 3 times. And then afterwards, the samples were dried in air, followed by the curing step in an oven at high temperature. And then the final developed textile fabrics were coated as the following, as shown in Table 1. For the characterization, we used a scanning electron microscope to study the morphology of blank and developed textile samples. TM images were also taken, and the mechanical properties and the Young's modulus was calculated using a tensile testing machine. The flaming properties were evaluated based on the fired based on average rate of burning using the fire testing technology. Furthermore, the hydrophobic properties were evaluated using a water contact angle measurement. So, the dispersion of TiO2 and peace in coating dispersion was confirmed using TEM images, and the morphology of the untreated and treated textile surface was investigated using SEM.
For the discussion of results, we will first discuss the morphological characterizations of treated fabrics. Here you can see a schematic diagram which depicts the synthesis of different materials. These materials are the graphite, GR, trimethoxylyl propyl ethylene diamine, TMSD, ammonium phosphate, AP, and TiO2 nanoparticles, and also the B solution. The dispersion of TiO2 nanoparticles in coating dispersion of the FTC4 was confirmed and showed in the next figure. The figure represents the dispersion and decoration of the TiO2 nanoparticles on graphite flakes. Figure A shows the TEM images of coating dispersion of FTC4 and its TEM image at high magnifications, while the figure B represents dispersion of coated TiO2 nanoparticles in coating dispersion and their immobilization on graphite flakes. Now for some SEM images. This SEM image represents the untreated textile fabrics which shows smooth surface of textile fibers, while this image shows that when the coating layer was treated on textile fabric surface, the fiber becomes rough. This reflected the coating layer containing graphite wrapped by ammonium phosphate and the TMSD, and finally wrapped with the binder chains. This image shows when the nanoparticles were involved in the coating layer. The nanoparticles were decorated on the graphite surface, which dispersed and coated on fiber surface and wrapped by B. While this next image shows that further clarified in high magnification of the SEM image of the FTC4 shows the dispersion of the TiO2 nanoparticles decorated on graphite and wrapped with TMSD and AP, and finally wrapped with the B layer. Next, we will talk about the thermal characterization of treated fabrics. These textile samples represents the thermogram of blank samples which decomposed in two decomposition steps. The first one was started at 280 degrees Celsius, which could be attributed to the composition's allulose chains of fibrin and wool chains. The second one was due to the decomposition of polyester and microfilament chains, which started at 391 degrees Celsius, achieving maximum weight loss at temperature of 436 Celsius as indicated in the table below. It is important to note that the improvement in thermal stability of treated textile fabrics clarified mainly from the enhancement in onset decomposition temperature of the main step is an addition to the enhancement in the maximum temperature. The next one will be the flammability properties. The flammability properties of untreated and treated textile fabrics were evaluated based on rate of burning, which reflects the flame retardations in textile samples according to the modified ISO standard 3795. As you can see on table number 3, the untreated textile fabric was burned with the recording rate of burning of 118 mm per minute and the LOI of 18.2. However, when the coating layer was coated on textile, the rate of burning was reduced, achieving 90 mm per minute, which indicated a higher LOI value of 21. It is important to note that in this study, the flame retardancy action was mainly attributed to the formation of char layer, which was the result of action of released phosphoric acid in conjunction with action of silicon and nitrogen-based TMSD, which provided a good char layer composition. Furthermore, the existence of graphite in platelet structure in the coating layer is very important because it supports and strengthens the formed char insulting layer structure.
Hi, my name is Aaron Tuanyo and I'll be continuing the report in results in discussion, particularly in tensile properties and hydrophobic properties. So here, the mechanical properties of blank and developed textile fabrics were evaluated and tabulated in this table. The tensile and elongation of untreated textile was 535 Newton and 29% elongation respectively. It consists a Young's modulus value of 0.5 Newton per millimeter squared. However, when smart coating layer was applied on the textile surface, the tensile strength was enhanced and achieved a 638 Newton as indicated in the table FTC1. In contrast, the elongation was reduced and the Young's modulus was enhanced. This might be due to the decoration of GR platelets on textile fiber surface. The tensile strength in FTC2 was further enhanced with a whopping 748 Newton, which is roughly a 40% improvement. Also, the elongation was improved compared to FTC1. This associated with decrease in Young's modulus reflects an increase in elasticity. In FTC3 and FTC4, the tensile strength and elongation was almost similar to the blank sample without any loss. This is associated with decrease in Young's modulus indicated improvement in elasticity of developed fabrics. This enhancement in tensile strength observed in developed textile might be due to the existence of GR platelet structure which is decorated on fiber surface. Also, it is noticed that the incorporation of TiO2 or the titanium dioxide nanoparticles maintains the tensile strength and improved elongation and elasticity of developed textile fabrics. So moving on to the next, we have hydrophobic properties. The figure above shows digital photos of water droplet in textile surfaces. On the left, FTC1 and on the right, FTC2. The hydrophobic properties of blank and developed textile surfaces have been evaluated. The study of water repellent property which results in self-cleaning property for furniture textile is very important. The blank textile recorded 0. However, when coating layer was applied, the morphology of textile fibers was changed to rough in conjunction to reduction in surface energy. This is due to the wrapping of coating layer on surface changed their surface morphology and the incorporation of silane-based material in the coating layer. This results in good hydrophobic behavior of the surface of FTC1, which achieved a 125-degree water contact angle and 145-degree water contact angle on FTC2. However, when AP increased and the titanium dioxide nanoparticle in the coating layer failure in hydrophobic properties in FTC3 and FTC4 samples were observed. This might be due to the change in surface morphology and surface energy of textile fiber surface. So lastly, in conclusion to our report, furniture textile fabrics were coated with novel thin coating layer. The mass ratio of ammonium phosphate was optimized. Titanium dioxide nanoparticles of an average size of 20 nanometer were dispersed in the coating layer and their effect was investigated. Thermal stability for developed textile fabrics was enhanced. The flame retardancy of coated samples was significantly improved with maintaining good mechanical properties. Rate of burning and LOI of treated textile fabrics were improved, achieving 0 mm per minute and 24.3 respectively. Compared to high flammability of untreated sample, hydrophobic properties of treated textile surface were enhanced, achieving 145-degree water contact angle. Flame retardancy and action of the developed textile was investigated and discussed.